For a deeper view, let us check the autonomy of a neural network. As the name suggests, neural network is consisting of multiple perceptions. And if we review the structure of a perception, it is not difficult to understand. You have several inputs, which are the attributes of the data, and for each of the attribute, we allocate a weight, and we multiply the value of the attribute with the weight, and sum takes the summation of all the products of all the attribute weight product. Use the result to do the prediction, and that is what perception do. For a neural network, we allocate multiple perceptions. Each of those perceptions share the same set of attributes from the data, but each of those perceptions has its own set of weights. For example, if you have 5 attributes per data sample, and let us say we have 2 perceptions. So each perception needs 5 weights to be associated with the 5 attributes of the data, and the 2 perceptions totally need 5 times 2 weights. And these 2 perceptions, of course, produce 2 outputs, and that set of perception combined with the input of the data is called one layer in a neural network. If we take the 2 output of this particular layer as the input and carry this entire construction procedure over next step, that is, we take the 2 output as the input to the next set of perceptions. In the next set of perceptions, each perception has 2 inputs. For example, we have, let's say, 3 perceptions in the next set, and each of these 3 perceptions has 2 inputs. So totally, we need 2 times 3 equals 6 weights to specify the next set of perceptions. We stack these 2 sets of perceptions together. We will have the processing schedule like, given the 5 attributes of the data, use the first set of 2 perceptions, convert this set of this data into 2 intermediate attributes, and then use the next set of 3 perceptions, convert these 2 attributes into 3 outputs, and this processing step is what a neural network do. Actually, there is no theoretical limitation on how many layers we can stack into a neural network. In practice, generally we can employ multiple layers to process data and to perform multiple steps of transformation. Mathematically, this is called function approximation. So, which means we would like to mimic the behavior of a function from the data input to the desired target of predictions. By function, we mean a kind of relationship of arbitrary complexity, and neural networks is very good at approximating or mimicking the behavior of such functions. and it's very useful to data analytics. Back to our Python implementation of a neural network. Let us investigate the multilayer perception classifier, which now it's clear that why we call it multilayer perception. And for this neural network, let us say its internal structure. So if let us have a look at this object. The attributes of an object in Python can be accessed by using the object name followed by a dot and followed by the attributes name. For the multilayer perception, we know the coefficients or the weights connecting different layers of input to output, different layers of the perception are called coefficients. So remember this underscore, that means something that is to be used, supposed to be used internally. But in Python, we do not have the concept of private members like in some programming languages such as C++ or Java. All attributes of all data member or method of an object can be accessed and investigated. But to respect the privacy of some objects, we have some convention such as underscore meant to be used internally if we interfere with those attributes of an object. Sometimes if the implementation is by a third party, the object might not work as expected. So says this said, at least let us have a look at those coefficients. To investigate an object or attribute, generally the first step is to have a look what it is. We can see the type of the attributes. I do not print it directly because it could be quite a messy big thing, and it's not easy to find anything just to mess up my notebook. I don't want this to happen, so have a look at the type first. So it is a list, right? If that is the list, we can check its members. Let's see how many elements in this list. 2, that's good. And now let us have a look at its first members type. Oh, which is good. It's something we are familiar with. That is an array of NumPy. Note this ND, that means n-dimensional array. That means NumPy array can handle high-dimensional objects, which could be very useful in data analytics, but it is not our focus at this moment. Let's have a look at this array. We call it array instead of ND array for simplicity reason. The shape of this array, well, that is 4 and 100. Let's try not to guess the shape of, guess the meaning of the first coefficient set. Instead, let us print out all its coefficient set shape. So that is more, it contains more, is more informative. So we can understand why there is a 4 in the shape of the weights, because we have 4 inputs. Remember, in our flower data, each flower has 4 attributes here, and We can also understand why there is a 3 in the second set of perceptions, because there are 3 classes of the flowers, right? And if you have watched the first part of the video, which is quite lengthy, but at the last part, I explained internally a classifier, a neural network classifier, represents the classes using class codes. So instead of representing class as 0, 1, and 2, it represents class as 100, 010, 001, like the binary code of the classes. So in each of the code, 3 classes are represented by 3 bits, and these 3 bits corresponding to the output of 3 perceptions. So what this 100 means? We can guess, perhaps, that is, we have 100 perceptions in the second layer. That layer is hidden from us, it's transparent for us. As the user of the classifier, we only consider our focus is the input and the output. So not surprisingly, those layers is generally called hidden layers of the neural network. In this case, the neural network has 100 perceptions in the single hidden layer. So the information passed from these 4 inputs to 100 hidden layer, and in the second stage of processing, the information passed from the output of these 100 perceptions in the hidden layer to the 3 output of classes to be predicted. But where does the number 100 comes? Okay, if we investigate a little bit more in the multi-layer perception classifier, let's check the help function of help document of the function. So, which is clear here, we have the option of specifying the hidden layer, and that parameter accepts a tuple. I suppose it also accepts list. This tuple, it has the default value of this tuple has one single element, that is 100. So I suppose if you use the default setting of this classifier, it will result in a neural network object contains a one hidden layer of 100 perceptions. Of course, this parameter is here for us to adjust. How about let us say, for example, let's say we have another multi-layer perception classifier 2. That has the structure as we just discussed in the in our discussion of the structure of neural network. It has one hidden layer, and in that hidden layer it has 2 perceptions. If we create such a neural network classifier and fit this classifier to the data train x, train y, and then let us check what kind of internal structure this classifier will have. mlpc2.coefficients. Now I'm quite confident in printing all the coefficients out. Why? Because I have a single hidden layer, and in this hidden layer we have only 2 perceptions. So I suppose from the input and the hidden layer perception, we would have the coefficients of 4 by 2 from 4 inputs to 2 hidden layers, and from the hidden layer to the final output we will have the attributes of 2 by 3. Okay, let's have a look. Yes, this coefficients is a list, and in the list each element is an array, and each array, for the first array, it contains 4 sets of weights connecting 4 inputs to the 2 hidden layer, and the second set of array contains how to connect the 2 hidden layer output to the final output of 3 classes. A neural network processes information according to its structure. For example, in this neural network, when the 5 attributes of a data sample is given, those attributes are given in this, we call it input units. From, for example, for such attribute, it is combined to the weight to each, linking this input to each of the neurons in the next layer. This is not surprising, as we discussed. The combination means to multiply the value of this input with the weight on this link between input and the neuron. For each neuron, it collects such combination of input and weights from all the inputs here, and take the summation as the total input to this neuron. And this procedure goes recursively from the input to the hidden layer. If you have more hidden layers, it can go all the way until we get the output of the network. There's only one thing we need to take care of this process. That is, if we represent this computation carefully, we can actually represent all the calculation using matrix multiplication, which I will show you some reference to if you are interested in the mathematical details. You can derive it. But the problem is, if you think about the matrix multiplication, they are associable. That means if you multiply matrix A and matrix B and matrix C, actually you can do the multiplication by multiply A, B, C, those matrices first, and then do your multiplication according to the matrix, the product of matrix A, B, C, instead of multiply them individually step by step. If we project that calculation to the operation of a neural network, that means if we consider the final total input to this neuron, we can mathematically combine all the calculations in previous steps. No matter how many hidden layers there are in the neural network, we can combine all those calculations in some weighted combination of the original input of the neural network. That means the total input of this neuron can be computed directly from the original input. We can call that the collapse of a neural network. That calculation renders all the internal layers useless, which is not the purpose of designing this step-by-step transformation of information. So where is the problem? The problem is we can associatively combine linear combinations That means if we multiply input with some weight and multiply it with another weight, we can combine all those multiplications together. How to introduce more complicated transform that cannot be collapsed, that cannot be summarized in some trivial multiplication. The way to do that is after we get the total input of each neuron, before the neuron output is we call it activation. We do a nonlinear transformation. So instead, for example, for this neuron, instead of output the linear combination of all its inputs directly to the next layer of neurons, this neuron perform a nonlinear transformation. If we talk about that, this may sound high-tech and complicated, but the specific nonlinear transformation is not as important as the fact that transformation is not linear, as long as the conversion from the input and the output cannot be summarized as a straight line, a curve. A straight line, it has curvature in the project from the input to the output. The entire structure of the neural network can be preserved. Previously, people use some kind of curve called sigmoid curve. Those curves squeeze the entire real number in between 0 and 1. For example, let us introduce the graphic functions as we do in the last tutorial. The command for that is pylab. If we include an inline, the plots will be drawn within this browser. I introduced this command in one of our tutorials, but I don't think I have introduced in details to all students. So, as we shown the example of nonlinear map between input and output, let's have a look at the graphic functions, which is provided by Python. It can be useful to realize data. For a map to work, we need the input and the output. Let the input to be x. We want the x to be something like -10, -9.9, go all the way to positive 10.0. To generate such a sequence, NumPy provides us a convenient way. We can use NumPy dot called a range, that is to generate a sequence in a range and put it in an array. Note, range itself is a Python standard Python function. It can be used to generate integer sequences. But NumPy's version of this function is more powerful. It allows us to generate sequences with float numbers. Start with -10, and the second parameter is the higher end of the sequence, that is +10. Because at this end it is non-inclusive, so we put a little bit more to this end, and the step size, let's set step size to be 0.1. Okay. Now we have our x ready. Have a look at the x. If you use, okay, also note that if you use Python 3, in all those examples, you need a pair of parentheses for the printing functions. Okay, let me just add these parentheses in case confuse anybody. We print the first 10 elements in the X as expected. Okay. Now let's consider a function y. Let us first consider the most the simplest function of y, that is linear. So let's have a look what a linear function should look like. Perhaps we have some shift. Okay. Now we also have y. And we can consider the relationship between x and y by plot x against y. This function will put points in two-dimensional plane with the horizontal axis the position on the horizontal axis to be a point in x, and the position on the vertical axis to be a point on y. And so to be more explicit, we can give the horizontal axis some name called x, and that is obvious. We call the vertical axis to be y. Let's run this cell. And we have a straight line. Actually, this straight line is made of points in the two arrays we have allocated. We can let the plotting function also show the points along which it draws the line. So we can use this representation to specify the way it draws. The first character represent the shape of the marker. We can use a dot. We can also use a ring, a circle. Well, we can also use a triangle pointing upwards, or triangle pointing downwards. Well, this looks a little bit arbitrary, but we can check the meanings and all the available samples in the documentary. For this example, I would use small circles, and the line itself, I'd like to use solid line to represent line. Of course, you can also use dots or broken lines. Okay, now we use just solid lines. Well, this is a little bit too dense, but if you consider that these are the points on which you draw, maybe we can use a slightly smaller marker. A little bit better, but not very much. But you get the idea, okay? Sure. Then we will try to have some nonlinear maps between x and y. For example, we can let y to be some nonlinear function of x, such as let y1 equals np dot power. That is to take the power of an array element y's. Let it to be the power of x, 2, 3. Let's see what we will get in this case. We can plot x against instead of y, but against y1. Well, this is another curve, and that is nonlinear. But that might not be a good idea to put this nonlinear map in neural networks. Look, because as the x increases, the y value increases much faster than x. This plot was not drawn proportionally. It has already been scaled so that it is convenient for visualization on the computer screen. Look, the range of the horizontal axis is only 10 plus 10, 20, but the range on the vertical axis now reaches 2000. A commonly used nonlinear projection is instead it's a little bit confusing, but let us join it first and understand the philosophy behind its design. Sure. That is exponential, okay, minus x. That is 1 plus, okay. Execute this one and draw x against y2. Well, this is much more manageable. Look, I'd like to take more notes on this. Remember, the note allows us conveniently take some the markdown cells allows us to conveniently take some mathematical notes, because y is defined by frac means fraction. The denominator is 1, the denominator is 1, denominator is 1 plus exponential minus x. So this is the equation. This is the equation of the function. If we consider this equation more carefully, we will find when x is very small, for example, it's minus infinity, we will have the double dollars means we want the equation to be in a separate line. Okay, y is going to be so this question mark, because x well, let me show this a little bit easier. Right arrow. Okay, now much better. And this is another right arrow. Good. The question mark here, consider that when x is going to be very small to the minus some minus quantity, and the quantity itself is large. So in this equation, the minus x needs to be a very large quantity, right? So this 1 plus exponential and the power to the exponential is large. So the result in the denominator needs to be very large. If you put 1 over some very large number, I'd like to see, let me put minus 9999 here to show the derivation. And so I would like to say the 1 is over some large number. we would arrive 0 when x goes to some minus value. Go to the when x travels to the minus direction, negative direction on the x-axis, y is going to achieve 0. On the other hand, no, not vice versa. On the other side, we can see when x goes to be very large, say it plus infinity, and now we have only one minus, and this denominator is going to be 1 plus very small number, and the equation will give us number so that the y is going to be 1. And there is something in between. When x is exactly 0, this case y would be 1 plus exponential to the power of 0, whatever to the power of 0 is 1. So that is 1 over 1 plus 1, that is 1 over 2, and that equals 0.5. So now the relation is clear. We call this function to be a squeezing function. Whatever x is, x could be some real number in whatever range, but this map will squeeze the output of a neuron between 0 and 1. This property is particularly useful in data analytics because in many cases we cannot be very sure about the scale of the attributes of data before we put the system into application. And such kind of function can guarantee that after one layer of processing, the output in the hidden layer is within some reasonable range, and that can give us some idea on how to initialize those weights for the model. Okay, and if we observe the plot of this function, we can see that when the x is to the negative direction, the value of the function approaches 0. When x approaches the positive direction, the value of the function approaches 1. When x is 0, is almost it is exactly 0.5. We can actually, I think we have a function called grid. We can turn on the grid to have a look at the function's behavior, but we don't have do not have a line here to show exactly the 0. And well, there's a lot of function analysis in the graphical part. This is not the focus of this course. There is another course called data visualization. Perhaps you can learn one thing or two from there. And there is a lot of tutorials, examples in the document of matplotlib, matplotlib, as we have introduced last week. I can assign the ticks. The ticks means the numbers on which it will indicate the functions on the y direction. Let it include 0.5 exactly, so we can have a clear look. Perhaps minus 0.0, 0.25, 0.5, 0.75, and 1.0. Okay, we assign the ticks before we draw the grid. Oh, now it is clear that when x 0, y is exactly 0.5.